again. Okay. All right. So welcome. So the first thing that I would like to do is, of course, it's continuation of the reflection refraction business. And we are going to do a couple of exercises for you to sort of like revise what we did last time. Plus, we are going to put this into work and then sort of like look at the connections with the actual device that actually apply the reflection and refraction in real world. Okay, and that will be the last stuff that we are going to do today. But before we move on, I think there's one thing that I would like to sort of start this lecture with, and I think I forgot to do in, I mean, I did like 50%, but I forgot to do the other half on the other section. So I have to do it on this Thursday. Okay, guys. So I'm going to switch to the simulation again, the one that we used to use it before. And I'm still sort of like encourage you guys to try this. It's the old physics again, and then I am in the topics of light. And as you can see, there are many subtopics in this categories over here that you can actually check it out. It's kind of very cool. And I think the library of this topic is kind of like growing over time. So, but I think at this point, I think we have most of the stuff that we really need for our topics in 102 here. And I am in the topics of reflection and refraction. This is the one that we saw last time. So we're just gonna sort of do a quick sort of like review what we did last time. So now this is a nice thing is you can adjust the incident angle. Okay, I don't know if do I need to increase this a bit. All right, that will help. Okay, so what we have over here is you can adjust your angle of incidence over here. All right, and you can see you always have to make a measurement of that angle with respect to normal line that's showing in the dashed line right there. And the good thing about this one is it's pretty sort of like complete in the sense that, see, there is like a faint, like a grayish line over there, give you a reflection. As we discussed, there is always like a partial part of the light every time that you have the changing the medium from one to the other. At the interface, not only you get refraction, but you get also all the time, actually you get reflection. But the intensity of the light that get reflected is only like a partial, maybe like 5%, 7%, on and on. Okay. All right, for those of you that are doing physics, actually, if you like do electromagnetic theory in maybe third year or something like that, then you have a chance to really calculate the percentage of the reflection and transmission. Okay, but for us, okay, let's say it's somewhere around there. Okay, and then you can adjust the index of refraction, as you can see. All right, and one thing that you can see right here, all right, if I sort of like go crazy with the bottom material to have like a super high N over here, you already learned that the incident angle, if you make a big one, then the refracted ray will make a smaller angle according to Snell's law. Okay, cool. So far, so good. All right. And then what you have over here is, and now you can adjust the incident of angle. No problem. All right. And first thing first, if you come in at 0 degree, nothing is going to happen. Everything is just pretty much like go straight forward. And the reflection is still there anyway. All right. And then once you keep increasing your incident angle, the refracted angle will increase, but of course it's going to have a smaller size than the incidence angle. That's fine. Okay, so no problem. You can increase until you hit 90 degree and that's it, pretty much it. Okay, but on the other hand, if you have a different case, the opposite case, when you have the upper material have a larger end than the bottom one. Now, when you start from 0 angle, okay, nothing happens. But then if you keep increasing, according to Snell's law, the refracted angle will be bigger than the incidence angle. So that means the light will bend away from the normal line. So if you keep increasing the incident angle, keep increasing, now you can see that the refracted angle is getting larger and larger until eventually it's going to hit. I'm just gonna do it like 0.1 at a time, right there. All right, it's gonna hit it at some point. All right, you guys bear with me a little bit here. All right. Oh shoot, am I going way too far? There you go. 45, 40 something, and this one is pretty close to what we had with the diamond air pair. Oh, actually, if I do that, that will be nice. The diamond is about 2.5, 2.6. And if I turn the bottom one to be air, let me move it to 1. Here we go. And last time we learned it, that's like I told you, like it's about 42 something, right? So let me move it somewhere around there. Let's see if I get that correctly. That no, it's not. Did I get, oh, 24, sorry, 24, sorry. It's a diamond air, right? Not glass air. Okay. So as you can see, right, if I start from, okay, let me start from like 20. And then if I keep increasing the incident angle, 21, 22, 23, here we go, somewhere here. All right, so maybe I sort of remember it incorrectly, but it's 20 something, 24 degree that you start to get total internal reflection. Okay, cool, guys. That's it. All right. That's, at least if you have here, it's I think it's a nice simulation for you to try. And I will just, and you can actually verify it using Snell's law. They have to calculate the whole simulation using Snell's law underneath anyway. All right, guys. So it's a good, and I think it's a quick review of what we would like to do here. All right. Any questions so far? Okay. If not, then I'm just going to stop this one and we'll get back to our slide over here. There you go. All right, so let's do some examples and do some calculation, shall we? All right, you're still having fun, I hope. All right, guys. So this one, you have the ray of light is perpendicular to the face AB of a glass prism, given the index of refraction to be 1.5. Find the largest value of the angle phi, which is just the apex angle on the right there, so that the ray is totally reflected at face AC. So you want the total internal reflection to happen on that hypotenuse there. And given that the prism is immersed in air, so it means the surrounding environment has the value, the index of refraction to be 1 in that case. So let's take a look at it. What happened? N equal to 1 case. And let me call it with the G, like making it out of glass, to be 1.5. Okay, first thing first, you hit it with the light. So the light, actually, if you see over here, you making 0 degree incident angle. With me, guys? So that means in the first interface, the face AB doesn't do anything. The light will just keep going. Just keep going. And it just hit the AC face. Okay, oh, it's kind of like off a little bit here. Sorry. There you go. All right. So in the first surface, nothing happens. Just go straight through. So what will happen next is going to be something that's going to happen on the face AC. So what you need first is just draw a normal line. That's the one we always use. There you go. That's a normal line there. Okay, so now you have to make sure that the angle that you will be using in the Snell's law is going to be the angle that made with respect to that normal line there. So let me call that theta. Okay, and now you apply Snell's law at a point of contact right there. And now, because you want things to happen given in from the problem, you want the total internal reflection to happen at that point. So the way that you do that is just you impose the boundary condition, the one that you're going to cross over from having the reflection or not having the reflection. So what you have over here is you just take that condition of having the refracted beam to make a 90-degree angle with the normal. Does that make sense? Okay, so that's what you have to do. And then you just apply the Snell's law. Let me call this point P then. So you say at P, what you have is sine, okay, let me start with the N glass sine theta, that's on the glass side, is going to be equal to the N air, which is just 1, and then you put sine 90 into it. Does that make sense? Is it good? All right. Now N air is 1, sine 90 is also 1. So over here, what you get is going to be the sine theta equal to 1 over 1.5. You're almost done here because they want to figure out the phi, the apex angle of this prism over here. And now you guys know from geometry that if the angle is phi at the apex of the angle by similar triangle, the one that next to the theta is also phi. So that means you can put the sine theta to be sine 90 minus phi. which is just cosine of phi. And that's it, guys. Taking this, you can write this one as like 2/3 on and on. And then you should be able to figure out the phi using calculator. Okay, guys?
Okay.
Not bad. This is all right. Yeah. So the part B there, they said, okay, what if you, instead of having this prism in air, you immerse this in water? So all you have to do is just make sure that you just change the medium around this one to be water. So there's nothing new at all. The condition that you still need around, around at the point P there, at point P there, you still need the same configuration there, which means the refracted beam is supposed to make a 90-degree angle with normal. Cool? All right, the only thing that is going to get changed is just the end that you're going to use. You just replace N of water in the position of N air, and you will be done. And that's it, guys. So let's do that. Part B, at the same point, you have, starting from the glass, it's going to be Ng sine theta. Now out there, the second interface is going to be in water, but you're still using the 90-degree refracted ray anyway. Okay, so now in water, you can look it up in the table. Let's say it's about like 1.3 there. Sine 90 is 1. The theta is 90 minus phi. So you can turn this one into cosine phi as well. So it's going to be 1.3 over 1.5. And you should be able to figure out the phi there. You are done.
Okay.
Okay, cool, guys. Not bad at all. Okay, this topic here is just Snell's law. That's it. Okay, the only thing that you need to understand a little bit more is just whenever you want the total internal reflection to happen, that's the border lines, the one that you're going to cross between you get the total internal reflection or not, is by setting the refracted ray to be at 90 degree, and you are done. Cool? Not bad. All right, let's move on to the next one. Any questions so far? This one is good already. All right, next one, it's going to be something that looks like the one that it's supposed to show up in the exam. And I think at this level, it's not too difficult, but it's like not super like simple, like plug and play. So I think this is something somewhere, I think just about right to be qualified in the problem in the exam there. All right, so let's take a look. In the figure, a light ray enters a glass slab at point A on the top there at incident angle theta 1 given to be 45-degree angle. So and then it undergoes total internal reflection at point B, the one on the left interface there. What minimum value of the index of refraction of glass can be inferred from this information? Is that cool, guys? So once again, they want to just have, like a minimum value of the end of glass. And you guys know, if you hit that minimum value and then you somehow have a glass that have a larger end, then you guarantee that you're going to get easier for you to do the total internal reflection. Does that make sense? All right, because we kind of understand it from the example of like glass and diamond and sapphire. The larger the end, the smaller the critical angle, and it's easier for you to get total internal reflection. Okay, all right, so that's kind of like in that kind of area there. Okay, guys, so how are we going to proceed in this one? All right, you have two interfaces, right? You have sort of like the Snell's law have to be applied at 2 points. So you can start from the top one. Let's look at point A. Okay, and once again, Snell's law apply at a point. So you can consider point A. At A, what happened, guys? Well, you say, okay, John, you have incident angle to be theta 1, everything is perfect. The angle is already measured with respect to normal line. So you can use that angle right away. So you can say it's coming from A. So you start from NA, and then you take the incident angle to be theta 1. So that's done on the left-hand side of the Snell's law. Now you equate that with on the way out. If you look here, I can say, okay, John, I don't know what this angle is, but I can call it the alpha for now. Okay, and then we're going to figure out later what the alpha should be. So what you can do is you can call it in glass. Let me use G for that. So I have a subscript G for that, in glass, and then I can do sine alpha. That's it. Okay, let me call this equation number 1. Just leave it there for now. Okay, so you have a couple of unknowns right now, in glass and the sine alpha that you don't know. All right, or you can substitute some known value into it if you like. That is fine. Okay, but that's your first equation that you have up there. Now, let's move on to point B. So now at B, what happened, guys? So over here, so don't forget, you have to draw a normal line to the interface first, all right? That will be your reference pretty much. So I'm just have to draw this one here. Okay, now what is your incident angle now? So you say, okay, that incident angle is gonna be this angle now, right here. Okay, it's the angle with respect to normal line. And because if you see this one, these two dashed line there give you a right triangle. So if you already said the upper angle is alpha, the bottom one is going to be 90 minus alpha. So that's good. Just use that one. And let me write nicely there. Okay, and that will be your incident angle. Now, what about the refracted angle? We already said, if this is supposed to be like a, initial configuration or the initial value of the configuration that will start to give you total internal reflection, what you would do here is just you assume that the outgoing ray make a 90-degree angle with the normal line. Is that cool? No, okay.
Okay.
So if that is the case, then now you apply Snell's law right away. So at B, start from glass, shall we? Yeah. In glass, sine 90 minus alpha. Cool. Equal to, now you go out into the air. So it's going to be in air and then sine 90. All right. Just plug in the known value in glass you want to figure out. Sine 90 minus alpha, you can turn it into cosine. In air is 1, sine 90 is also 1. You can call this equation number 2. All right. So if this is it, I mean, if you have a calculator next to you and you want to do it, what you can apply right away is you can just, let's say I just take 1 divided by 2. Okay. And what you get over here is you can say that n glass will cancel. You guys see that? Here? Okay, so if you take equation number 1 divided by equation number 2, you will be left with just sine alpha over cosine alpha. In glass cancelled. On the right side, you will have 1 over sine 45. Sine 45, you can write it as like root 2 over 2 if you want. What you get from here is the 10 of the alpha is going to be, what you can flip it over is just root 2. And then you should be able to get alpha out of this. Once you get alpha out of this, then you can just plug in into one of the 2 equations that you like, and then you can solve for n glass. You are done. Cool?
Okay.
Not bad. Right. Or some of you might, if you want, like you do some analysis on it without using calculator. But Ajahn, I remember the trick. If you have sine alpha and cosine alpha, you can eliminate that alpha by using identity if you want. So you can sort of apply this identity that sine square plus cosine square is always equal to 1. All right, you can do that too. So this means you square equation number 1, you square equation number 2, and then you just take just the sine and then the cosine square terms, add them equal to 1, and then you can solve for n sub g right away if you want. So that will be fine too. Cool. All right, that's another way of doing it, and just your preference, whatever you want. Oh, there's a question comes in. Why can the equations at for point B can be divided? Oh, okay. You can manipulate equations whenever, whatever you like. For example, there might be in the future some cases you might want to take equation number 2, subtract by the equation number 1, on and on. So when you have equations and you would like to solve for the unknowns, it depends on how you want to manipulate. You can do any algebra to those equations. Does that make sense? And the reason that I picked the division between the 2, because I want to eliminate the n sub j. Okay, let me write it here. So there you go. So I look at it and I say, okay, I have n sub j in both equations. And if I take equation and then divide it by second equation, that n sub j will just cancel out. So I will be left with just a single unknown, and then I can solve for that first. And once I solve for the first unknown, I can plug it back in to figure out what should be the second unknown, and I'm done with the equation solving process. Okay, does that make sense? Okay, all right, guys. So I think that's pretty much conclude the reflection and refraction. Now, what we are going to do next is Oh, there's a more question comes in. Okay, wait a second. Oh, can we do all this? You can apply these techniques everywhere. Yes. Whenever you have two or more unknowns, then you must do some manipulation to the equations that you already set up. Yes, you can do all the time. This is think of it like a mathematical procedure. So it's mean it doesn't have to follow any physical laws or anything. It's just manipulating the numbers there. Yeah, you can do it anytime you like. Okay. Okay, very cool. All right, now, so what we are going to learn next is, now we already had these two in my bag. In our bag here is the reflection and refraction. So we're thinking about it. Okay, hey, what is kind of like, stuff that you sort of like looking around and then you say, hey, sort of like have this built in and then there's sort of some utilities or maybe some applications out of this. And is there anything that we can, put some model and do some calculations in it? And that is about the image formation. So this is kind of like, I don't know, have you done this before? But the topic about image formations already pop up like back in maybe middle school problem sometimes. And definitely in high school, some of you have already done some calculations. So that would be nice. But for those of you that haven't seen or haven't done any calculations on this, so think about this one. So the way that you see things is just when the light hits your retina, right? That's how you see things, right? When you look around and you can put things in focus, you watch or you're seeing things clearly. So it means there must be some light hit your retina in your eyeballs there. Okay, but now when you say hit, it means it has to hit in some sort of like some way that you make your image or whatever the things that you are seeing looks in focus, right? When you say in focus, I mean everything is sharp, it's clear, and this is what happened. Think of it this way. If you have an object, you want to take a look at this object, okay? So there must be some light coming out from this object, and eventually it's going to get directed to your retina in your in your eyes. Sorry, not your ears. Okay. All right. And the concept looks just like this. So at every single point on the object, so I can mark like a red dot right there. So you can imagine that, I mean, there is a light coming out of it, even though the object might not be like intrinsically generate light by itself, but there must be some, light sort of flooding the object, and then the objects just reflect all the light out. Okay. So you can imagine that that red dot right there has some light coming out of it. Okay. So that's why you have to turn on the light in the dark for you to see things. If you turn off the light, there's no light that's sort of shine onto the object. There's nothing reflected off the object. You won't see anything of it. All right. So that's what the point is. Now, if you can imagine that the red dots emit light, so you can draw rays of light coming out in all directions. So that's the light would just come out in all direction. Okay. But we only care just some of it, just for us to be able to analyze where the light should go. So what you are doing over here is just like, okay, Ajahn, I'm just going to check some light, some rays of light. So let's take a look at the ray number 1 on top. So look at this one. All you need to do is just trace the rays. Light's always going in a straight line, correct? So it's just going to go, go like that, just go straight. But now let's think about it. What happened if you hit some surfaces and you change the medium? So once the medium's changed, then you always have to apply either reflection or refraction all the time. In this case, let's say this is lens. You guys know lens, right? So it's just like a transparent medium, but then the shape of it is curved. So that means at the point of contact over here, the light is trying to penetrate, transmit into the other side. But because you are hitting the surface at some angle, so actually what you have to do is you have to apply Snell's law right here. Seriously. Yeah. So you get the refraction going on in the first interface on the left. And now once light gets bent a little bit, it's enter in here. And now on the way out, they want to get out into the air again. You have to apply Snell's law one more time at this interface. Does that make sense, guys? So that means every time that light tries to transmit through a lens, it just have to do that to refraction. But overall, we don't care much. All right. We don't want to apply like Snell's law twice. What we care about at this point is, let's say you change the direction of rays. That's it. So on the way out, let's say by the shape of this lens, it's made it so that the ray actually come out in the different direction here after the lens. Does that make sense, guys? Okay. And that it's going to hit some point, but I mean, the light will just keep travel. Just forget about that one. But now you say, let me do another analysis, okay, with different rays. We're just going to take a look at some different directions of light. So let's take a look at maybe the ray number 2. Okay, right there. Let me pick like the other one. All you need to do, just do the same analysis. So the light will just go straight out from the source. Just keep going. Hit the first interface, get bended a little bit. Hit the second one, bend it a little bit. But at the end, it just come out in some direction. Okay, and then you can keep doing this. Maybe ray number 3, you do it, lights coming out straight. Okay, hit the first interface, get bended. Second interface, get bended. It's bended inward like this. You can do, as many as you like, but it turns out from this configuration here, you can see that the outcome of this refraction make the rays converge into a point. You guys with me here? Down here on the right side. So that's the point of convergence right there. So you can say that these rays are crossing each other at this point. So you call this a focal point. Does that make sense? So it's a point of focus. So anytime that you have a focal point, it means you can think about it in your head. It's just like you mapping the red dots on the left into the red dot on the right. See, so you transfer the information or something like that. So whatever the red dot is on the left, showing up on the left, you can look exactly, information and everything will be showing up on the right. And that's why we call this the image. And this is how image is being formed. Okay, you guys with me now? And this is the thing, that's why you so seriously talking about the focal point, because if you take the screen and then you put somewhere in sort of like, a little bit further to the front. Okay, so you probably put it here. So as you can see, the light will just not in focus yet. All those rays will just hit random, not random, but at different spots on the screen. So this one, you're going to get a blurred image because the information is sort of like gets washed out a little bit. So it's still unclear where it's supposed to be. All right. And if you get so, crazily like so close to this one, then it's going to be super blurred because all the red dot was just being spread out even further apart. So does that make sense now? So that's why the image formation is when you look for the point of the rays crossing. And that's when the image of the object is going to be formed there. Cool. All right. And in this particular case, the lens is doing the job of redirecting the rays until it's by its points of intersection. And our job here, we just try to find a way that, hey, Ajahn, how can we calculate the position of the image once we have an object placed in front of a device? And this device is called lens, based on the refraction of light. Sort of see the whole picture here? Okay. That's what we want to do. All right. Now, there is another device that instead of using refraction, you use the reflection. That's possible. It's just a mirror. Of course, Ajahn, I've seen that. Okay. So what you have over here is just, instead of having refraction going on, you have reflection. Now, let's take a look at what happened. If you once again have a source, I put the red dots in there. And now all you have to do is just, just trace out a ray based on reflection and refraction law, right? So let's do it one more time. Let's do it. Let's say ray number 1 on top. You just, okay, John, go straight, nothing happened. Once you hit the mirror, you get the reflection. Now it's a mirror. By the law of reflection, the incident angle equal to the reflected angle. So the ray will just reflect back like that. Okay, no big deal. That's done. Now let's pick another ray, shall we? So let's do the bottom one here. So let me call this the ray number 2. Underneath there. So let me use the green one. The light will just come out. Nothing happened. Now hit the mirror. Now you do the law of reflection, things will just get reflected out over here. What do you see here, guys? Look at the direction of the rays. It's actually diverging. See that? It's actually getting this way and that way. They're never going to cross. No way. So what happened in this case? In this case, will you see something here? Well, whatever you see is not going to be a real crossing of the rays because ray is now diverging, right? They're never going to see each other again in their lives somehow, I hope. All right, if there's no other devices to direct everything back. So what happened to you is this. When you place your eyes here, don't forget the ray will just come out like this, right? So you will have a diverging rays all over the place. It's just diverging ray, diverging rays, diverging rays, diverging rays everywhere, yeah? But then you place your eyes there. Your eyes and your brain working in synchronized way that every time that the light hits, there is like a sort of internal structure of the light focus everything into your retina and everything. But the point is, your eyes and your brain will interpret every time that when the light hits your ears, the object is in the front. There's no way that your eyes can interpret like a curved light hit your eyes and the no, that's impossible. So every time that the light hits directly into your eyes, your brain will interpret that the objects are in the front. So over here, your eyes will perceive in such a way that they will see that actually you can extend that rate of light. And once you extend those diverging rays, they're going to have a focal point that appear to your eyes. Does that make sense? All right. This is what you will see. So you are seeing the image of the object. So the red dot here still show up here on the right, exactly the same because that is a focal point. But because this focal point appear to your eyes only, not by the actual rays crossing. So this is also focal points. But now the image you're seeing over here is not a real image. You guys read me now? So what I'm trying to say is what you're seeing up top, that's real because actual rays are actually intersecting. Bottom here, no, it's just a virtual image. So this is the reason why every time you look at yourself in the mirror, you see yourself, but you cannot touch it. I mean, you cannot grab it. You cannot do anything with it. You cannot put a screen behind. You cannot do anything behind the mirrors, of course. But the image of you through the mirror, you cannot do anything with it. You only see it. That's why that is a virtual image. In contrast, if you look at the real image, this is the one that actually you can touch. When you say touch means you can focus the image onto your palm, in the palm of your hands, or project the image onto the screen that you, when for example, from the projector in front of your classroom, for example, you can project those images onto a screen. Yeah, something like that. That's real because the light is actually, being put on the screen. Cool?
Okay.
All right. So, I mean, maybe I talked too much already, but that's what I'm trying to distinguish between what does it mean by the real image and what does it mean by the virtual image and what does it mean by a focal point. Why focal point is so important? Because it's the point where you map out the information from the source, from the object, and exactly duplicate that into the side of the image. Done? Cool?
Okay.
All right, guys. So that's the classification of the types of images that you can form. Okay, and there are two types of the device that we are looking at over here is the lens and is the mirror. Lens doing the refraction to generate image. Mirror using the reflection to generate image. That's it. All right, when I say that's it, I mean, now we have to dive down further if you really want to calculate exactly where the image is being formed, what type of image you're going to get, and plus the size of the image might not be exactly as the object, okay? So let's start from something simple first. Talking about mirror, the mirror is easy. When you just look at the mirror is flat. So when it's flat, everything is simple. See, this geometry is nice. That is just like, that's why we say a mirror image, because everything is symmetric across the mirror, left and right. It's just a reflection. So that's why if that is the case, this is a simple image formed from a plane mirror. It's just a flat mirror. So what you get over there is if you place an object in front of the mirror, you can call that the distance from the mirror to the object distance. Okay, guys? Cool. All right. And you can use any notation you like. I don't know, some of you that have already done this. Sometimes they might use the P, sometimes they might use the O, sometimes they might use the S, sometimes they might use the U. All right, anyway, but it's just the object distance. And now because it's just a plane mirror, everything will just get reflected to the right. So it's just symmetric. It's just like you flip everything, just, do the mirror image. Then your image will show up at exact same distance. And that you're going to call this the image distance. Cool. All right. You can use the I over here. You can use the this is an object, and that's I is good. I don't know what pair that you guys use. S prime, the V, I don't know. There's so many things that you can use. All right. But anyway, just imagine that there are only two things. It's either the object distance or the image distance. And for just the plane mirror, the concept is simple. The object distance equal to the image distance. Cool. All right, that's easy enough. All right. If you want to look at this one, you know that it's going to be a virtual image because light never going to go through the image. I'm sorry, go through the mirror. Light never gonna find itself behind the mirror. That's impossible. All the light must get reflected, right? That's what it has to be. So, I mean, everything will just bounce off from the mirror surface. So nothing should show up behind the mirror. So if you see the image show up behind the mirror, it's guaranteed, I put a big word here, it's going to be a virtual image. And that's what it is. Cool. All right, but this is an easy one. It's just it's like a plane mirror, nothing special. Things start to get a lot more fun if you look at the curved mirror. Whenever you have a curved mirror now, law of reflection comes into sort of like a main stage over here. You have to now figure out where the light rays will eventually cross, right? So now you think about it, oh, John, if you want like any curved mirror, your life will be tough. And that will be a real like geometric optics there if you have like a super special curve mirror. So we're gonna do a simple one. Let's do a spherical mirror. Why do we like that spherical shape mirror? Because of this, guys. Think about it. If you have a mirror that has a spherical shape, and now you send in a ray that is parallel to the something we can name it like a central axis. So think of it like you have like a reference line crossed in the middle of the mirror. And then you send in the light in the horizontal direction. The easiest way to think about it is just you doing the laser beam, like a laser pointer. You just point the light beam into a curved mirror. But because we would love to have this one to curve in a spherical way, and every time that you have the reflection or refraction, every time we do the normal line, right? We have to draw a normal line. So imagine this, what will happen with the normal line, guys. It's a mirror that is sphere, or think of it in two dimensions, it's a circle. So every time that you draw a normal line perpendicular to the surface, where should it hit? Of course, it's gonna hit the center of the circle. You guys with me?
Okay.
Right, that's normal lines. Yeah, normal to the surface of a circle will hit the center. The good thing about that one is, so when you come back and take a look at the law of the reflection, guys, bam, you have the incident beam angle, bam. Now you're gonna get the reflected beam coming out of it with the same value of the angle across that. And now you see that, hey guys, the normal line hits the center of curvature. So wherever this thing will get reflected, it's going to be half of that distance. You guys with me? So what I'm saying is, if the center of curvature here, this is your radius. Okay. So whatever this rays that going to cross the central axis there, it's going to be half of that. Because of the law of reflection, you chop your angle in half. So the distance will be chopped in half as well. So that's how you can imagine where the light should be. Because if you do the same analysis to the bottom ray, okay, I can call this the number one ray, and then you do the equivalent ray in the bottom, the ray that coming underneath parallel to the central axis will get reflected here and bounce up, and they're going to cross at the focal points, guys. That's it. That's your focal point, is just waiting for you there. Cool. And that's where you can, now I got it. That will be my focal point. And now with that, I can name this distance from the focal point to the center of the mirror to be my focal length. Focal length. So it's a distance from the focal point to the center of the device. And that's it, guys. So that's how we define the focal length of a mirror or lens in the future. You just figure out what happens when you send in a parallel beam of light, and then it's eventually going to get focused down into a point. The distance from that focal point to the center of the mirror is going to be your focal length. And now we know in the spherical case, the focal length will be half of the radius of curvature. You are done.
Okay.
Cool, guys? Here we go. Now, let's look at the other way. Well, Ajahn, that's kind of nice and cool. Everything just curve in the direction that light eventually going to cross exactly what I mean at the focal point. But what if the curvature go the other way around? So look at the figure on the right. Now it's curved backward. Think of it that way. So what you have here now, when you send in the exact same light beam parallel to the central axis, hit that surface of the mirror, they're going to bounce off. But now it's going to be diverging rays, just like what we saw before. But then if you extend that ray of light, they're going to somehow cross at one particular point. Yeah, so that's your focal point, just like before. And then if you measure the distance from that focal point to the center of the lens, you still have the focal length, just like before. And from the law of reflection, one more time, if you draw a sort of like a normal line to this one, of course, Ajahn, that normal line still has to pass through the center of curvature, just like before. Nothing new, but it just now reflects off in the divergent fashion instead of converging down. So what you have over here is now you're going to have a focal point behind the mirror. So sometimes you can call this one a virtual focus, a virtual focal point. Why? Because the point that you're looking at now is behind the mirror, where the light shouldn't be. Light already get reflected and diverging. So what you have here is you got it from extrapolate the rays to this point. You guys with me now?
Okay.
Extrapolate means you just extend your rays in your imagination or whatever. All right. So in this case, you get focal point and focal length just like in the left hand side case, except this one you're gonna have the focal point and focal length in the opposite direction. Cool, but still the focal length still half of the radius of curvature anyway. So what you have over here is on the left, we can call this type of mirror to be a diverging mirror. I'm sorry, converging mirror on the left. So on the left side, you have a concave. I don't know, sometimes you confuse about it's called concave or not. You can sort of confirm that by saying this is a converging mirror because it's converging light into a focal point. On the other hand, on the right hand side, you have a convex. It's a noon. It's convex. Or easier one, you call it the diverging mirror. Okay. And the concave or the converging mirror, you saw it every day if you look at your satellite dish. The satellite dish is exactly the one that's using as a concave or converging mirror because you want to converge the electromagnetic wave from your satellite and converge it into the receptor at the center of that dish. You see that there? That is a satellite dish. There, I should have like an actual figure there, but there is a device here over there. So assume that that satellite dish is sort of like receiving the radio signal or electromagnetic wave from the satellite and focus everything onto the receiver at the center of that dish. The same thing here. Okay, guys, that's kind of like the application that you can see here. All right, so what we have for you Well, Adan, okay, I got the point and everything is fine. What happened if instead of having the lights coming from in so far away, you have a parallel beam of light? You place an object in front of these converging or diverging mirrors. What should happen? Yeah. So let me grab the scenario for you right away. If you used to use this kind of thing, I don't know how to call this properly, but I think it's like a cosmetic mirror, something that will just blow up your face like 5 times or whatever. And then you can do makeup or you can do whatever fine detail on your face and other stuff. This is going to be your, it looks curved, right? It's concave. It's concave, right? So that's one application that you probably have seen. Another one that you probably see as the opposite case is the convex, the diverging ones is the one that you saw at the street corner. So when you have a mirror that allow you to see the other side of the street, any incoming cars or not, that is your convex mirror in use. But if you notice over here, the image that shows up in both cases are not exactly the same as the size of the original object. The one on top, it blows up, the image is sort of enlarged, so you do a magnification, okay? But in the bottom case, at the street corner, you can see that the image on that mirror is going to be smaller, get squeezed down, is tiny stuff, but allow you to see more. So that's what it is. So the key is what happened to the object in the front. You have to figure out where should be your image. Does that make sense now? Yeah. And now, of course, your object can be placed anywhere. It could be any part of it. So this is what we are going to do after the break. So what you are going to have to do is you place an object here in front of the mirror. You call it the object distance. Let's say I can use P, I think, because the textbook eventually use P for that. And then you would like to figure out where the image should be. That is your image distance. Does that make sense? But of course, it could be that the object is in the front, but the image might show up in the back. That is fine. So that's what we are going to calculate. Given that you know the focal length of these mirrors, how can we calculate that? Plus, we also want to know what type of images that you're going to get. Is it going to be inverted like this? See, the object is right side up, but the image is inverted. Or it could be like the object is just up, your image is also up. So we want to have a way that we can sort of like signify what should be the final image. Is it going to be inverted or just like right side up? Everything is fine. And the last thing is we want to know the magnification. So in this case, you see, oh, Ajahn, is this height is this big here, but your image is just that tall, so it's getting smaller. So you get some reduction in size. So this one happens as well. But the one that you saw in this example here is the enlargement of the image and all this stuff. So how can we figure these all out? That's going to be after the break. Sounds like fun?
Okay.
All right, guys, take 10, and then we'll figure out the equation that allow us to calculate everything here, guys. All right, guys. So what you can see over here is, if you have a chance to play around with this, this one is the concave mirror. This simulation allows you to adjust the focus here, and so that means you're changing the focal point of the mirror, and it is, I think the curvature of the mirror changed a little bit too. It's kind of nice. Okay, and you can play with the size of the object and the location of the object. All right, and as you can see, all right, let me start from the far away. Yeah, on the left, you guys follow here, right? So what you have here is now the object is quite far away. And then if you follow the upper rays there, where the mouse is pointing there, hit the mirror and it's bounced down somewhere. And in this case, because you have just a horizontal rays, the reflected ray is going to pass through the focal point. But now you can just, I mean, all you need is just finding out just one more rays, right? Because you just want to know where they are going to cross. So you can pick another rays if you like. Look at the middle one there. If you trace a ray going through the focal point, see that? Now you can guess what should happen afterward, after hitting the mirror. Of course, it's going to bounce out horizontally. So, I mean, the light is just travel in a straight line. So that means if you go forward and it's bound in one direction, you can just reverse the arrow, everything just go backward. I mean, no doubt. So that's what it is. So this is going to give you a horizontal reflected ray. And just by looking at the top rays and the middle rays, you know where they are going to cross. And that is the image location. And you're done. You guys with me? Okay, that's kind of cool. I don't know if it's cool or not, but that's what it is. Or you can trace another ray. That's another easy one. If you trace a ray that actually going through the center of curvature, that's a CC right there. Once it hits the mirror, it's going to bounce back on itself because it's going through the radial direction. When you move along the radial direction, hit the surface of the circle, you're going to bounce back exactly the same because you hit the surface of the mirror perpendicularly, which equivalent to 0 incident angle. And that's it. So you can pick one of the two of these three. They're going to cross at exact same points. All right. And now from here, you can sort of play around with this, adjust the location of the object. If you move the object closer and closer and closer, as you can see, now the image is getting away from the mirror a little bit, and then you might cross. Doesn't matter. But the thing is, what you can see at the end is the image location is still in front of the mirror. So you can say right away, this image is real. Cool? Because it's an actual, it's the real rays crossing. And now you can look at the sizing. If you're far away, the size of the image is small and it's inverted image. And if you change the location of the object, the location of the image will change as well. And in this case, you still have a real image and it's still inverted, but the size of the image is now larger. You get some magnification here. Okay, cool. All right. Now, on the other hand, if you get even closer, whoa. Now, see, you see the flip here? All right, let me try to make it that it's getting the image location getting further and further away, further away, further away until it's off the screen. And then if you still move object closer now, you get it closer than the focal length. You see the dashed line on the right there? That's the extrapolated rays. So that means now you can look in the front of the mirror here, the ray that get reflected now it's diverging. You see that? So here, you're never gonna get the rays to cross each other anymore. It's diverging rays. So the only way that you're gonna get the image out of this is going to be a virtual image, those extrapolated rays on the back. And see now the image is upright, magnified, behind the mirror. See, I told you, if it's behind the mirror, it's definitely going to be a virtual image because light can never travel back behind the mirror. It can never get back there. It's impossible. That's not possible. And this is the scenario of that cosmetic mirror, the one that you saw when you move your face very close to that mirror there, it's magnify your face, and that's the magnification that you get. Your image is sort of get larger. You get like a blown up image of your face there. Cool. All right. So this is, I think, is a very good utility, good simulation that you can check it out. All right. And then you can adjust your focal length, focal point, everything. You can get focal point far away, or you can even flip it backward to give it like a convex mirror. And I don't know why convex means it's just behind it, but it doesn't have the mirror that go the other way around. I don't know why. It just disappear. All right. But I hope it's just like, if it's in the front, you have a concave mirror there. There you go. All right, then. Oh, is it? This one cannot be moved. I don't know why. Okay, guys. So I think this is going to be a very useful simulation for you to, get some sort of like a visualization of things that we are doing at this point. Okay, but then of course, Ajahn, in reality, who will do this? I mean, sort of like, you have simulation, you have everything, but we really want to get to the place where the image is being formed. I want to calculate exact distance. I want to calculate the magnification. I'm going to get like how many times bigger or how many times smaller. That's our business of the equation. We need an equation there. All right, let me stop the simulation here and then get back to our calculation here in our slide. Okay, you guys still having fun? I'm not so sure. All right, guys. So what we have to do here is now we need an equation. Let's start from a simple one, guys. The one that is simple to do is just the equation of the magnification. Why not, right? Because of course, I mean, if you want to know the magnification, what can you do? Just measure it. So what you can do is the magnification can be defined very easily. Just take the image size divided by the object size. When you say size, it just means the height in this case, because you have like a one-dimensional problem. So over here, the sizing mean is just the height. So the h represent the height of the object, and the h prime is just the height of the image. All right, so that's an easy sort of like way of defining your magnification. However, in reality, you need to have some relationship with other things too. The good thing about this one is it turns out this ratio over here has the close relationship to the ratio of the object and image distance, believe it or not. It turns out to be equal to the image distance over the object distance. Nice. That's kind of cool. All right. Make it sort of like relatable to things that you can eventually gonna measure. However, I would like you to sort of like take the other equation other than this one. This one has an absolute sign here. So and then when you have absolute, so you lose the information about the sign. So what I like better is this one, guys. So let me call this equation 1 star over here. So this is the one that I really like because it has a negative sign in the front. It might look annoying. However, the good thing about this one is if you take this equation and plug in the numbers that you're going to do in a near future here, along with the sign that attached to each parameter, both Q and P, your final value of M, including the sign, will tell you everything about this. When you say everything is this, if the M give you a positive number at the end, then it means you say right away that the image is going to be upright. Isn't that cool? Okay.
Okay.
And if the M that you got is going to be like negative value, you can say right away it's going to be inverted. This is so cool. All right. So I prefer to have you sort of like take the equation that has a negative sign built in. It's much better. It can use much clearer and you don't have to think much at the end. Okay. That's the first equation that we need. The second one is we call the mirror equation. And I think you might have seen this before, but if not, it's not that bad. It's just the inverse of those parameters that we mentioned to you and introduced to you before the break. You can see this, the inverse of the object distance, 1 over P, plus inverse of the image distance, 1 over Q, equal to 1 over focal length. And that's it. You're done, guys. We only need these 2 equations and then everything will be fine. Seriously, everything will be fine. So what we're saying over here is the only thing that you need to know how to apply this equation is just apply the correct sign. That's it. The difficulties of this problem is just sign assignment. You just have to assign the correct sign to each terms. Plus another benefits of this one. If you understand this, you will automatically know how to work with the lenses. Seriously. All right. So take my approach. I don't know if this one works or not. You can take a look at this table and, compare the sign, what should be a positive value, what should be a negative value. But my approach is this, guys. Look at this. We already agree. Mirror reflects light. So think about this one. First, let's take a look at the object. When you have object staying in the front somewhere, okay, you have an object sitting somewhere. And then you want to measure the distance from the object to the mirror. You call it the P, right? The object distance. As long as the object is in the front, the P is supposed to be positive because that's your common sense and measurements and everything is real and everything is good. So as long as you have only a single device, either the mirror or lens, your object distance is always positive. Cool. Plus, you can call that is the front side of the mirror or the front side of the lens, because that's where the object is. Cool. All right. So that the business about the object is kind of like obvious. Usually, most of the time, you will get positive object distance. All right. There will be some complex system that you will find yourself in the negative object distance, but that will happen next lecture, not today. All right. But for now, if you have only single device, either mirror or lens, The object distance, it's always positive. Okay, now look at the image now. So for the image, you guys agree with me already. Light reflects from the mirror. You will never find light behind the mirror. That's not possible. That doesn't make sense, right? So that means if the image is about to show up in the front, when I say the front is here, this is the front. This is what I can call it. It's going to be the place where light should be.
Okay.
Right? Light should be here. I mean, you should find the light in front of the mirror because of the reflection. And I'm going to take this one to be my positive side of the image. Anything that shows up here for the image, that's positive. And anything that shouldn't be, light shouldn't be behind the mirror. No, no, no. This is pretty much like forbidden. So this one, you're going to have a negative sign for it. That's it. That's my key concepts for all this mirror and lenses business here. All right, take a look at this. Let's see how to apply this one. Guys, where is the focal points for this converging mirror, guys? Bojan is exactly right here. That's my focal point. And where is it right now? It's in the front. See, so this means, I mean, if you shine the light into it, then everything should be focusing onto that point. It's in the front. That's why for converging mirror, you have focal point to be a positive number because the focal point is in the front. So the focal length is positive. Cool.
Okay.
Got my point here. Next, if the image distance shows up as a positive value after your calculation or whatever, let's say you show up, you have a positive Q, numbers that you got from your equation give you a positive number, then you can say that the image is going to be real. And the distance that you got as a positive means that the image shows up in front of the mirror. You are
okay.
Cool. Right, try this one in the bottom. See this? Diverging mirror, the convex mirror. The light hits it, diverge out, but you already agree with me that, hey, Adan, the focal point is behind the mirror. We already agree that anything that shows up behind the mirror, this is the one that light shouldn't be. No, 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 light shouldn't be here. So that's why you can say right away that the focal point it's behind mean this is virtual. So whatever the distance that you get from here is your focal length. So you can conclude that the focal length of a diverging mirror is going to be negative value. Done. That's the whole idea.
Okay.
All right. And let's take this along with us and I will show you how to apply this kind of agreement of the sign. And I hope by looking at just one simple exercise and everything will be clear. And if this is clear for you, the business of lenses will be a piece of cake. Okay. Chocolate cake too, actually. Yeah. Kind of sweet and sour, bitter a little bit. Okay. All right. So take a look at this one. You have a concave spherical mirror, has a radius of curvature to be 20 centimeter. All right. So now you are given the R, radius of curvature to be 20. So that's good. So you know right away that the focal length is supposed to be 10 centimeter, half of that. Find the location of the image for object distances of given value 40, 20, and 10 centimeter. For each case, state whether the image is real or virtual, upright or inverted, and what kind of magnification. So it just asks you to do everything pretty much. Yeah. All right, just do it. Let's say you only need 2 equations for all this business here. Let's start from the first one, shall we? So you already had the object distance to be at 40. Let's use P to be 40. And of course, it's positive because you only have a single piece of mirror over here. Now, the focal length, you already agree that the value of the focal length is 10. But then this one is concave. Yeah, the concave one is the one that it's an uppercase over here that where the focal point is still in the front. So that means you're talking about a positive focal point on focal length. Then it's going to be plus 10. You guys with me so far? And that's it. You know, 2, the last one is going to be easy to find. 1 over P plus 1 over Q equal to 1 over F. So that means 1 over Q is just 1 over F minus 1 over P. Substituting in the value, so it's going to be 1 over 10 minus 1 over 40. Everything I can emphasize that these two are positive. Cool. And I don't need to convert any units because, I mean, as long as all these three parameters using the same unit, I'm fine. All right, so work on it. You have, what is this? So it's going to have 3 over 40. Is that right? Okay. All right, it's still positive anyway. And at the end, the Q that you want to find out is positive 40 over 3. Cool.
Okay.
That's pretty much done. And then the unit you got at the end is centimeter. Now, what does it mean? It means, all right, let me draw what we have over here. There you go. All right, the focal length is here 10. Let me mark 10 here. The radius of curvature is C is 20. Okay, and your object is way here, 40. So it's going to be twice here. That's your object there. Okay, so at the end, what you got? You got 40 over 3. So it's, let's say, roughly about, what's that, 13.3 or so centimeter. So that means your image location will show up 13.3, but it's positive. That means it's here. It means, guys, positive means it's in the front of the mirror. Cool. So now you know where your image should be. Now let's apply the second equation, shall we? Okay, now I want to know the type of the images and everything. Oh, the type, Dan, wait, the type is already no. Because you have the image shows up in the front because you have a positive number right there, you can say right away, this is real image. But the type in the sense of the orientation of the image, all right, no problem. M equal to negative Q over P. Negative sign is there. The Q is 30 over 3. The P is 40. So at the end, you get negative 1/3. Cool. So what it means by negative 1/3, it means that you have 1/3 of the size. So you get the image reduction in size in comparison to the object size, 1/3 of the times plus, 1/3 times of the object height. And it's a negative sign means it's inverted. So at the end, what you get over here is, if I draw this one sort of like here, okay, here's your image. I'm sorry, here's your object. If it's this high, then your image is going to be here, inverted, but it's only 1/3 of the size. So it's going to be shorter. You're done. That's it. So the answer is real, inverted, 1/3 of the size. You're done.
Okay.
So you see how it's supposed to be calculated using the mirror's equation. Okay, try again, part B. Everything will look exactly the same, except now you move your object distance now to 20. Your focal point still at plus 10 centimeter. So your focal length is positive 10, and it's always positive 10 here. So once again, I can use 1 over Q equal to 1 over F minus 1 over P. 1 over F is 1 over 10. P is now 20. So now at the end, what you get is going to be 1 over 20. And that leads you to Q equal to positive 20 degree, not degree, sorry. 20 centimeter right there. Okay, so what you get over here in this case? Dan, you get the positive Q. It means that the image is going to be real. So this means your image will show up in the front. What about the magnification? But Dan, go ahead. M is going to be minus Q over P. Minus Q is positive 20. P is positive 20. It's negative 1. So what do you get here? You get pretty much exact same size as the object. And this one makes perfect sense because if you look carefully in terms of where this object is located, can you see? It's set at the center of curvature. You just place your object here. So from the law of reflection, you sit at the center of curvature, the reflection will just come back to yourself. So, okay, so that's why your location of your image is exactly the same position. However, because of the reflection, you flip everything upside down. So your image supposed to just go upside down there, but there will be no magnification or reduction in size. It's going to be exact same size as the object. Isn't that cool?
Okay.
Yeah, so these two equations pretty much tells you everything. All right, guys, last one, try part C. All right, same thing. P is now at 10. F stay exactly the same, positive 10. So your image location is going to be 1 over F minus 1 over P. And it's 1 over 10 minus, whoa. You get 0 out of this. So this means that your Q go infinity. What do you think is happening right now? Well, of course, Adan, you put your object right on the focal point. And everyone knows everything that come out from the focal point will reflect parallel to the central axis, just like this figure here. You with me here? So you're sitting here at the focal point. So everything that come out of it will eventually just go backward. You just reverse the arrow. So everything will just bounce off horizontally. So this means that imply that your image supposed to show up at infinity. But of course, it means that the light that coming out of it is parallel light. So pretty much you don't get any image here. So they're never gonna cross. So that's why you get infinity as your answer. All right, guys, isn't that cool?
Okay.
So that conclude pretty much how you apply these two equations. Okay, so you can think of it as like a mirror equations, allow you to figure out the position of your image. Where is it forms? Is it going to be real or virtual by looking at the sign of the Q? Second equation, the magnification. And I just ask you to just take it with the sign, the negative sign in the front. Good thing about having the negative sign here is the final results will automatically indicate the image supposed to be upright or supposed to be inverted. And the value of the numbers of M will tell you, is it going to be magnified in case of M larger than 1, or is it going to be reduced in size when M is below 1? And if it's exactly 1, it's the same size as the objects. You are done.
Okay.
Nice. Okay, I think this is easy to grab, and then the concept is pretty easy to follow. And then, the calculation is not bad, but conceptually, I think it's easier for you to look through the simulation. I think that's sort of give you a bigger picture. Yeah. But in terms of the equations, it's kind of like, yeah, not a lot for me. All right. So if you guys agree with this, now let me finalize this lecture by looking at the lenses. And you guys are going to see it's going to be super easy because it's just like the same business, but you just change your condition a little bit. Instead of reflection, you get refraction. So this means lens supposed to allow light to pass through. Does that make sense?
Okay.
So you're never going to get any reflection anymore. So look at this one. So the scenario will look exactly the same. Let's start from converging lens, shall we? When you say converging lens, you think of like converging mirror, but instead of do the reflection and then converge everything in the front. So you allow light to transmit through the backside of the lens and then converge into a point. See this? So that's it. So what you get here is this is your focal point of this lens. The distance that you get is still your focal length. And you use the same trick that you used before. It's not a trick, it's like agreement that we said, because nature of lens allow light to travel through it. So that means whatever happens supposed to happen behind the lens. Light's supposed to be here. It shouldn't be any other way. Light supposed to be here. So this is the place where you're going to call it a positive side for the image, for the lens case. And you shouldn't see any light in front of the lens anymore. No. So if somehow you get image shows up in the front, that's going to be virtual image. So that means anything related to the image that shows up in the front, that's unnatural. So you're going to get the negative sign into it. So I can take this one to be real, and this one is supposed to be virtual. And everything just go on just like a usual business here. There's nothing new. Yeah, let's take a look at how it's, I mean, how can I apply this kind of logic into assigning the focal length to these lens. See this? Where is the focal point, guys? Well, then the focal point is behind the lens. And because whatever behind the lens, we call it real, we call it positive. So that's why your converging lens will have positive focal length. Cool.
Okay.
Now let's contrast this with the other types of the diverging of the lens is the diverging lens. In this case, the light that hits the lens get diverged out. So the way that you can figure out the point of intersection is you have to do the extrapolations. So you extrapolate those diverging rays and you say, oh, it's virtually crossed there. So you can say this is your virtual focal point. Cool. And if you look at the distance over here, of course, this is going to be your focal length. But because now it shows up in the front where the light shouldn't be.
Okay.
Right, this is my way of saying, right? I mean, light shouldn't be, but it's kind of true, right? Light shouldn't be here. Light's supposed to already leave and then just, you know, go to your right-hand side and not supposed to come up in the front anymore. So you can conclude that your focal length for the diverging lens is going to give you a negative value. And that's the conclusion.
Okay.
The rest go as usual. Okay. Except now the positive side for the image, it's behind the lens. The negative side of the image is in the front. Okay. So my key concepts that's, I don't know would that work, but it seems to work for me is wherever the light should be, that's your positive side. Wherever the light shouldn't be, that's your negative side of the image. Okay. And just to make sure that in reality, even though in the textbook or whatever you want to draw lenses, you always draw this shape for the converging lens. But in reality, the lens might not have the shape like that all the time. The key point is you just make sure that the center of the lens is thicker than the rim. You always have converging lens. Yeah, it could look like this. It could look like that. That is fine. On the other hand, for the diverging lens, it might not look like this all the time, right? It might look like this. As long as your center is thinner than the rim, you always have the diverging lens. Like this one, the center is smaller or thinner than the rim. Center is thinner than the rim. And for those of you that wear glasses, and if you guys are nearsighted, so you have problem with your eyesight and everything, and then if you nearsighted persons, then you are wearing diverging lens like this. And as you can see, it's not in the shape as the first one, right? It's curved in the same direction. So your glasses more like this. This is where your glasses is being made. Okay, it's a convex concave type, but the center is thinner than the rim. So you can see that for those of you that has like a really, really super short nearsighted, then you can see that your glasses is going to be pretty thick to what, you know, your frame. All right, so that's what it is. All right, cool. So if you accept this kind of like, you know, logic of assigning the sign, let's give it a shot and see how it goes. Yeah. So use the simulation one more time. All right. So you can go back. I don't think I have to switch the screen anymore, but you can go back and take a look at the simulation, and then you can play around with the assigning the focal point, focal length, the location of the object, location of the image. But one thing that you can sort of like quickly take a look at this one. See? So if you have this scenario over here, the object is being placed on the left, and you found out that the rays are intersecting on the right where it should be. So this is your positive Q at the end. See that? And you can say right away, this is going to be a real image. And by relying on the magnification equation, you have a way to figure out how this is going to be inverted, and the sizing is going to be the M, give you the magnification value. See, cool. Try again. This. All right. So if you place an object here, somehow the ray just popping out like this is diverging, then we're going to cross. You have to extrapolate the rays, and somehow they are crossing over here, which is shows up in the front. So you know the Q that you get over here is going to have a negative value. And you can say right away, this is going to be your virtual image, because the image shows up in the place the light shouldn't be. So that's not going to be real. The only way that you can see this image is just place your eyes there. Just take a look at it. Okay, just I'm going to see it and then where it goes. Cool. All right, guys. So that's what's supposed to happen here. Then let's take a look at the calculation. All right. Oh, I'm sorry. This is just a conclusion of what I'm about to say. So we're gonna use the same equation. I don't know which one I call it, 1 star, 2 stars, but the key is just these two equations there. All right. And when you use this for lenses, you just call this thin lens equation. You might be wondering, why it has to be thin. The reason is because here in reality, the thickness is supposed to have some effects. Don't forget that lens requires 2 refraction. Okay, every time light hit the first interface, it refracts, and on the way out, it refracts again. So it turns out in reality, the thickness of the lens should have an effect onto the final focal length and some complication or other stuff that you need to calculate. However, if we can assume that, okay, but John, forget about that. Just assume that you have a fixed focal length, and let's assume that we don't have any thickness. So this means just like think of it like it has a single value here where the position of the center of the lens should be, and then apply this equation. If that is the case, and then you still use this equation, we call this a thin lens equation. Okay, because actually we have a thick lens equation, but I took it out. All right, just too much. All right, so just play around with this thin lens. I think that's good enough already. Okay, cool. All right, let's give it a shot and see how can we apply this thing here. So what we have here is an object is located 20 centimeters to the left of a diverging lens, having a focal length of 32 centimeters. Okay, let me draw a figure for you guys here. Okay, let me put it here. Diverging looks like this, but then we already got it like diverging lenses, John. The focal point is in the front. So your focal length turns out to be negative. So actually to be clear, you have to put negative 32 focal length into it. You guys with me?
Okay.
All right. So your focal length is negative 32 centimeter. Now, determine the location magnification of the image. Actually, we can locate everything. Okay. So I place object at 20 centimeter, but the focal length is already 32. So, I mean, I just place object somewhere here. Let's say, there you go. That's my object, 20. And because you have only single device right now, of course, this is going to be your P, which is always positive. No problem. Okay, so let's attack it. So conclusion, we have positive 20 centimeter for object distance. We have focal length of negative 32 centimeter. Now what you need is just finding out the Q. So once again, you apply the same equation, 1 over Q equal to 1 over F minus 1 over P. So far, so good. All right, and that gives you 1 over 32. Don't forget the negative sign there, minus 1 over 20. Cool. Now, you guys need to help me a little bit here. All right, so let me find out like the common denominator here. And what I'm getting at the top is going to be 52. And now I have to flip over a little bit to figure out the Q. Now you can see that the final value of the Q stays negative. Yeah, it's still negative, right? And it's 32 times 20 over 52, all right? I don't want to punch the calculator at this point, but the point is it's negative value. What does it mean, guys? It means, okay, can you approximate this? I would say it's about, this is like 600-ish. So let me say it's about 12 centimeter somewhere each. So that means your image will show up somewhere here. 12, but in the front. Why is in the front? The negative sign. So once you notice that it's negative sign, you guarantee that this is going to be virtual image. You guys with me?
Okay.
Okay, negative 20, I'm sorry, negative 12 means in the front, 12 centimeter. And it's definitely going to be virtual. Now, we want to figure out what about the sizing and, upright or inverted. So you apply M equal to minus Q over P, and it's going to be minus Q. You already got it. Take the whole sign along with it. Negative 32 times 20 over 52 divided by the P. P is 20 positive. All right, whatever cancel, I can do that. I just cancel 20. So I'm getting positive, and it's going to be 32 over 52. See that? Yeah. All right. So what does it mean? M positive means it's upright. And look at this one, it's less than 1. So it's going to be reduced in size by a little bit. Let's say it's about like, 0.6 or whatever. So what you have here is whatever the size of the object is, the image will show up in the front, upright, and about that 0.6, like 60% high. And you are done.
Okay.
Okay, so hopefully this one showcase what it means by you only need these two equations to figure out everything about image formation from either lens or mirror, and just stick with the sign agreement. And my rule of thumb is pretty easy. Wherever the light should be, that's where your positive image is supposed to be positive. That's where your image is supposed to be positive. And wherever the light shouldn't be, that's where your image is supposed to be negative. That's it. All right. And then you can apply this rule to both mirrors and lenses. Any questions so far? All right, guys. So if not, that is it for today.
Okay.
I hope you learned something. But it's way lighter than before, I hope. But wait for it. Once we're done with this optics business, then we'll get back to electricity and magnetism, and then the calculus will be back. Okay. You probably miss it already now. All right, guys. So take care, and then I will see you guys on Wednesday. Yeah. All right. Bye-bye. Thank you.